Everyone talks about power system inertia these days, but many discussions only tell half the story. Power system inertia is the kinetic energy stored in the rotating masses of synchronous generators connected to the grid. When a large generator trips or a major disturbance occurs, inertia automatically resists rapid frequency changes by releasing this stored energy into the system. The key point is that inertia does not stop frequency deviations, it buys time. It slows the rate of change of frequency, giving control systems the opportunity to react. First comes the inertial response, which occurs almost instantly. Then comes the primary frequency response, where governors, batteries, and other fast-acting resources help arrest the frequency decline. Finally, secondary response, typically through automatic generation control, restores frequency back to its nominal value and rebalances the system. This sequence has been the foundation of grid stability for decades. However, the global energy transition is changing the equation. As more conventional thermal plants retire and renewable generation increases, many power systems are operating with lower levels of natural inertia than ever before. Transmission system operators around the world are responding by deploying synchronous condensers, procuring fast-frequency response services, implementing grid-forming inverter technologies, and creating new markets for inertia and stability services. But there is an important nuance that rarely gets the attention it deserves: voltage stability. Industry discussions often focus heavily on frequency stability while overlooking the fact that voltage stability is equally critical for reliable grid operation. Synchronous machines provide much more than inertia. They also contribute reactive power, fault current, voltage regulation, and system strength. As these machines retire, grids lose both frequency support and voltage support. Voltage problems do not always announce themselves through frequency deviations. A system can maintain acceptable frequency while suffering from weak grid conditions, reactive power shortages, or declining voltage margins. This is particularly important in renewable-rich networks where inverter-based resources are replacing traditional synchronous generation. That is why modern grids increasingly require a combination of synchronous condensers, STATCOMs, advanced inverter controls, dynamic reactive power support, and grid-forming technologies. The objective is not simply to replace lost inertia, but to preserve the full spectrum of stability services that conventional generators have historically provided. The future grid will not be judged solely by how much renewable energy it can connect, but by how effectively it can maintain frequency stability, voltage stability, system strength, and resilience under all operating conditions. Inertia matters. Voltage matters. System strength matters. Grid stability requires all three.